Today we're going to talk about net change. And in this video, we're going to look at the difference between total distance traveled and displacement. I would like to start off by drawing a velocity graph for the particle. Here it is. The x-axis is labeled with t, which represents time in terms of seconds. And the y-axis is labeled with velocity as a function of time. As you can see, there are three regions on the graph, A1, A2, and A3. Notice that A1 and A3 are above the horizontal x-axis, meaning that they are positive regions, while A2 is below the x-axis, which means that it's the negative region of the graph. Let's say positive in this case means going forward, and negative means going backward, relative to the starting point of the particle. T1 and T2 are the starting and ending times for the time period that we are looking at for this particle. If we were asked to find the total distance traveled by the particle, we would sum up all of the areas, which means that we add A1, A2, and A3. Now, if we were to compute the integral for each of these regions, we would notice that A2 would have a negative area. And what does this mean? Having a negative area means that it moved backward during that time. But because it moved, we still need to take into account the distance traveled during that time. We can do so by taking the absolute value of the negative area and then sum up all of the regions. On the other hand, if we were looking at the displacement of the particle, we want to find how far the particle has moved relative to its starting point. This means that if it at some point moved backward, its displacement would have decreased during that time. In fact, if it ended up at its starting point, its displacement is zero. So how would we obtain the displacement from integration? Well, it is less complicated than finding the total distance traveled because you don't have to figure out when the particle changes direction. You would just compute the integral using the velocity function as the integrand and the starting and ending times at the interval of the integral. If acceleration is represented by a parentheses t, how would we find it in terms of velocity using integration? We know that we get acceleration by taking the derivative of the velocities. In order to undo the differentiation process, we integrate the acceleration as follows. In the next video, I'm going to illustrate these concepts using an example.